I'm Johanna Matthew. I'm an associate professor at the University of Michigan. I'm in electrical engineering and computer science. I actually do electrical engineering, not computer science, but we're one big department there. I'm also the director of our Institute for Energy Solutions, which is a cross-campus institute at the University of Michigan that brings together researchers on any energy topic that we want to work on together. So I was told to spend about 10 minutes talking about my background, and I was debating what to share with you, but we'll just start at the beginning. I guess the message that I wanted to convey is that there's different ways to kind of pursue a career or even a life, let's say, not just a career. Some people are very, very strategic and sort of figure out what they want and try to align and drive towards it. Other people sort of just take opportunities as they come and hope for the best, let's say. I would put myself in the latter camp. Like, I try to be open to lots of opportunities in life and see where it leads me. And so the path I will explain to you will hopefully also showcase that. For example, I'm an electrical engineering professor and I have no degrees in electrical engineering, so I can tell you I wasn't super strategic about that piece. So I grew up in a relatively small city in Maine. And I went to MIT for undergrad and I studied ocean engineering there, which was a somewhat random decision because when I was a freshman, I went on a field trip to the Woods Hole Oceanographic Institute. Do people know about Woods Hole, Louis? And I was like, oh, they're building these underwater robots. This is so cool. Let's explore the deep sea. And so I studied ocean engineering. But in my senior year at MIT, I did a capstone project, which was to design a wave energy harvesting machine. So we had to design and build a small machine that we put in the Charles River, which is the river that separates Cambridge and Boston. And we had to capture measurable power. So we built this thing over the course of the year and showed that we could do this. And the amount of power it captured was like milliwatts, hour scale. But it captured measurable power. I was like, oh, this is really cool. I can apply my knowledge to actually address energy issues. So that's kind of how I became interested in this. But I took a detour because after MIT, I was really burnt out and I didn't want to directly go and do a grad program. I'm not sure how many of you felt like that too, or if you all directly went into your programs. But I joined the Peace Corps and I went to Tanzania and I taught physics and math in secondary school there, which gave me a lot of interest in working in developing countries. So I applied to grad school when I got back and I went to Berkeley, where I worked on water treatment actually. Removing arsenic from drinking water in Bangladesh. And that's actually where I met your colleague professor here, Kurt Kornblith. So we just met this morning and we interacted years ago. And it's been a long time since I've seen him, but it was fun to catch up. So I was doing that for a while, but as part of that, I was also interacting with people at Lawrence Berkeley National Lab. And I saw that you have Art on your wall, Art Rosenfeld, who was one of my advisors. So one of my PhD advisors was Ashok Gadgil, and the other one was Duncan Calloway. So I was working at Lawrence Berkeley Lab on water treatment, but also realizing I missed energy and I was studying mechanical engineering, and I sort of missed math and didn't want to be doing chemistry. But no, so if you're a chemist, please don't take that personally. Just sort of, I missed that piece of it. So I decided to explore what I could do in the energy space, and this was in the late 2000s, after the California energy crisis, when Berkeley Lab had created this demand response research center to understand how buildings provide demand response when the state was experiencing high peak load. So I started working with all of these folks and I was like, this is really cool. This is what I want to do with my life. So I worked with them. I did my PhD, which I'll actually describe some of the work that led from my PhD afterward in my talk today. And then I did a postdoc at ETH in Zurich on electric power systems, because at this point, I had degrees in ocean engineering and mechanical engineering, and I wanted to work on the power grid and demand response, and I had no credibility in this space. So I did a postdoc in electrical engineering in Europe, and then I came back and became a professor at Michigan in this space. So that's how I got to where I am. And it's funny, I stopped 14 years ago when I started, or 12 years ago when I started my professorship. But since then, it's been a lot more linear, and you're going to learn more about my path since I've been a professor through my talk. So I'll stop there now. Any questions, thoughts, anything people want to share? Is that useful to hear backgrounds? Okay. Cool. Okay, so I will launch into my talk now. It's about distributed energy resources. And I just wanted to acknowledge the support from the National Science Foundation and also RBD. And I also wanted to show you a picture of my graduate students. This is actually a couple of years old now. This was my group 2 years ago. And we work on a variety of different research topics in distributed energy resources. So I characterize distributed energy resources as anything connected to the distribution grid that can provide an active resource to the grid. So it could be distributed generation like solar PV, or it could be backup generators, distributed energy storage like batteries or other types of storage, and flexible loads. So it could be things like using your air conditioner for a demand response event. I work on a lot of different topics, and so this just gives you a sense for the types of topics I work on. I'm not going to talk about them all today, but a lot of my work is not on the hardware, but on the software side. So it's about figuring out the algorithms to schedule and control different distributed energy resources to make them interact with the grid. So I worked on batteries, specifically using batteries to provide multiple services to the power grid to help balance the power grid. We've done something similar with solar power inverters. Commercial buildings is actually where I started my work in demand response. Grid scale batteries, we've looked at them providing high frequency services to electricity markets and then the impact on energy usage. And then also modeling and control of other flexible loads like air conditioners for ancillary services. So I'm going to talk about this one today, and I'll dig into what all of those terms mean if you're not familiar with them. And this is an outline of my talk. So first, I'm going to give you a background on distributed energy resources and how they can engage with the grid. And then I'm going to show you examples of how DERs can balance the power grid, and then talk about some of the challenges associated with doing that, and finally some conclusions. So first, the background. So specifically background on how these types of distributed resources engage in electricity markets. So let me just set the stage for what this looks like. So many parts of the world now have electricity markets where we trade wholesale electricity. California is a good example. CAISO is nearby. Actually, I'm meeting my student who just graduated, who now works at CAISO tonight for dinner. So she's your neighbor now. But there's a lot of different types of electricity markets. There's something called a capacity market that makes sure that there's sufficient generation in a system to provide peak load. There's energy markets where we transact energy, and loads buy energy and generators sell energy. And ancillary service markets are reliability markets that make sure that we can balance the grid in real time to make sure that there's no power outages. So that sells all the reliability products. In California, you have energy markets and ancillary service markets. I believe you do not have a capacity market, but other parts of the country do. So distributed energy resources could potentially participate in all of these markets, but this is very much up and coming. It's not common these days for distributed resources like rooftop solar PV, batteries, or flexible loads to directly participate in these markets. There are pilot cases, pilot studies, there are demonstration projects, and it's sort of all coming right now, in part because of some federal directives. But the way they do that is they don't usually directly engage in these markets, but instead they engage through something called an aggregator. So an aggregator is an entity that takes a bunch of small scale resources and makes them look like a big resource. How many people have heard of aggregators? How many people have heard of virtual power plants? They're basically the same concept. So I will tend to use the word aggregator, but you can also imagine this like a virtual power plant. So again, it's a resource that looks like a power plant that can provide services in these different markets and engage just like a power plant, but it's composed of a bunch of smaller discrete things that you have to control to get them to look like a power plant. So you can have an aggregator that aggregates different types of resources, like you can have batteries, solar PV, flexible loads, or you could have an aggregator that just aggregates a single type of resource, like just the flexible loads. So for example, an aggregator could be the company Google working through Nest thermostats to aggregate people's household air conditioning by talking through the Nest thermostat to get those air conditioners to do something collectively. Or an aggregator could be an electric vehicle company that then coordinates charging for different flexible loads. Okay, so how does that actually work? So the way it would work is that an aggregator wants to interact with the market operator or the independent system operator. This is the entity that runs the grid. So the example here is the California independent system operator. So what they would need to do is say, I have this big resource and I want to offer it to the grid as a resource. So I'm going to bid into a market. And then the market operator then dispatches the resource to do something specific for the grid. And this happens in advance of real time. So often day ahead or hour ahead, this transaction happens. And then after the aggregator is dispatched, they're ready and waiting to actually deploy the resource. And so the aggregator, in order to enable this, has to have a contract with different consumers. So the consumer could be a residential home, it could be the commercial building owner, it could be a big battery plant that's connected in distribution, et cetera. So the aggregator says, come join my aggregation. I will pay you for it. In exchange, for that payment, you have to follow my commands when I'm deploying commands to change power consumption or production for your resource. So in real time, that control or coordination happens, but the contract is negotiated in advance. So they agree on terms. And the consumer has a strong interest in protecting their equipment. So they'll also put in place constraints. It says you can't do this at certain times, or you can't do it too much because it might affect me. If the resource is a flexible load like an air conditioner, the consumer might say, I only want my house to fluctuate in internal temperature between this small range because I don't want to be inconvenienced. So that could be an example of a constraint. So this is kind of the lay of the land of how this actually works in terms of the coordination strategy. The challenges, if you're an aggregator then, are how do you design this bid and offer strategy? How do you offer the resource to the grid, which requires specifying how much flexibility you're offering and also how much you want to get paid for it. They also have to design contracts with each of the consumers to say, this is how much I'm going to offer the consumers for this resource that they're providing to me. And this is how I'm going to constrain what I can do. And they also have to design a control and coordination strategy. How in real time do I actually deploy this resource to behave like a virtual power plant? And so most of my work actually does this third one, focuses on the control and coordination piece. So when you dig into DER control and coordination, if you want to coordinate different distributed energy resources, you have to figure out how you're going to do that. What kind of mechanism are you going to use for control? So you could send electricity prices, make the price high, it reduces consumption, increases production, make the price low, vice versa. Or you could send commands, you could say turn off, turn on, move to this state of charge. Or you could set instructions that are even more complicated like that. For example, you could say like, if do this specific thing only if you can do it because your current operating state is here. You could do something more complicated, but that might give the DER more flexibility in their response. Okay, so those are the many ways we can coordinate these DERs. Prices, a lot of people say we should do everything with prices and markets. We should deploy electricity prices that change over time, and we should get responses from resources based on prices. However, price response is less reliable because people have to be paying attention to the price in order to respond. And there's also the possibility that you could get synchronization through prices. If everybody's seeing similar high prices at the same time, everything could change their production or consumption in the same way. So you have to be careful of that because synchronization of behaviors across DERs can also lead to physical oscillations in the power grid where the voltages start to swing and the currents start to swing, and that could actually lead to a blackout if you did it very aggressively. And there have been papers that have shown that. Commands or instructions, when you're more explicit and you're kind of more direct as to, I want you to turn off or turn on, or do this thing if you're in this state, are usually more reliable, but they need the consumer's trust because many consumers don't want to give that level of control over to an aggregator. So those are the different options. When we think about capacity and energy markets that I mentioned before, where you're ensuring sufficient capacity in the system to provide generation, or you're buying energy, any of these options may be possible. But if you're looking at ancillary services markets, these are the ones where you're trying to ensure reliability of the system. You need a very highly reliable and accurate response. And so commands or instructions are usually better because you can as an aggregator guarantee the response a bit better. So that's what I would argue here. There's a lot of caveats to this. You could also say, well, what if I send prices but I automate the response? And so I know what the response will be because the price response is automated. I would say that actually looks like a command and not a price anymore, but people think about this differently. Okay, so before I start to talk about my actual work in this space, I just wanted to provide this note. So I said, recall the DERs include distributed generation, storage, flexible loads. In this talk, I'm going to use flexible loads in almost all of my examples. I've done work on storage and also solar PV, but I'm going to talk a lot about air conditioners, water heaters, and things like that. So as far as I'm concerned, all the ideas I'll present today apply broadly to all DERs, although the specific instances of the models, the parameters, and the formulations may have to change based on what you're looking at. But I'll give you a lot of examples about loads, but make sure that you're also thinking, oh, this could be a battery, or this could be solar PV as well. Okay, so back to the outline. So let's talk about some examples of how DERs can balance the power grid. Feel free to raise your hand and interrupt me at any point. This doesn't have to be me just talking at you, and I'm happy to stop and answer questions throughout. or just take them at the end, whatever you prefer. Okay, so how can we balance the power grid? So when we think about loads in particular, helping balance the power grid, most people think about demand response programs, where you have a load responding to a signal from the grid because the grid needs a load reduction usually. And so there's a lot of work on this about using different buildings to provide these types of load reductions, which are called load sheds. This is a paper I wrote a very long time ago, and I was still a grad student at Berkeley with people from Lawrence Berkeley National Lab, where we looked at how 3 different buildings were responding to critical peak pricing in the state of California. And the way those programs worked is that during these hours between 12 and 3, the prices went up 3 times, and between 3 and 6, they went up 5 times to normal price. And so it incentivizes load sheds during those hours. And you can see the baseline is what we assume they would have consumed if they hadn't tried to respond. And the actual is what they did consume. And the difference is the residual. So you can see there's a load shed here and a bigger one there. And those are 3 different actual buildings in California. The furniture store is the IKEA in Palo Alto, East Palo Alto. So you can see a lot of people work on this sort of load shedding. Load shifting is also something that we have buildings do to help balance the grid. In load shifting, instead of just reducing load, you're trying to shift it to another portion of the day when it's less critical that you reduce. So in this case, there's actually, this plot's a little confusing because there's 2 different baselines that they're showing. The green and the blue are both and the red is what it actually did. So it's pre-cooling. It's cooling the building before so that it can ride through the hours. Is that what you're gonna ask? Yep. Okay, yeah. And then this is also an old paper from LBNL. And you can see there's 2 baselines because we never, baselining is a modeling activity and you never know what the actual baseline is. You never know what the building would have done if you didn't control it. So you can only estimate it. So that's a really important research topic. Go ahead. Yeah.
How do you evaluate the effectiveness of these measures when you look at the comparison between like what actually happened and your prediction?
The effectiveness in terms of the response to the event in this case?
Yeah, like I guess you've got what happened, you've got what you think will happen. How do you know if like you got what you wanted to happen?
Exactly. So a lot of people compare to the baseline and then estimate the amount of, in this case, shift that you got and compare it to what you were trying to achieve. Maybe they didn't actually have a target for a shift, but they just wanted a shift, and then they can say, well, how much were we able to shift? A lot of people also do research on the accuracy of baseline models, which usually involves creating the baseline for days where you know the counterfactual, like the building didn't do anything and you're predicting it not doing anything so that you have the ground truth. And then if you know that error, you can also say, well, that's about as much error as I would also assume here in my baseline. And that can give you an estimate of the error from the shed or shift. So I don't know if that fully answers your question, but a lot of people are like, when they do this type of analysis, they're looking at like, how much did the building respond? But I know that my answer is uncertain. How do I quantify that uncertainty?
Yeah, it does answer my question. I guess that it invites more about the difference between shifting and shedding and how you measure them.
Yeah.
The difference in evaluating those.
Yeah. Did you have a question?
Yeah, when you possess solar panels and you're producing energy, if you have an oversupply of energy and you want to give it to the grid through a contract, would you be considered an aggregator, or do you have another status within?
If you have solar panels and
Yeah.
you're trying to give them to the grid.
Yep.
So normally a home or a business would have an interconnection agreement, and they would do that individually. You could aggregate a bunch of solar panels and have them being controlled, which means being curtailed strategically by an aggregator as well to provide reliability services to the grid. So it could go either way, but the second case I just explained is much less common. Yeah. So I would say load shedding and shifting are the old way of thinking about this. The way we think about this now is a much more active type of control paradigm. So in the other case that I was showing you, we were sending an open loop control signal to these resources, these buildings, and having them do something, and hopefully they respond. This is showing a simulation of a feedback control where we're having a bunch of, in this case, air conditioners collectively try to track the output of a wind farm. So the wind is going up and down, and the air conditioner consumption is trying to go up and down with the wind. And then this is in simulation. This was by Duncan Callaway in 2009, where he was showing that this was possible and that we should be using these resources in more advanced ways because they could do a lot more for the grid by doing this level of balance of the grid. And this was actually deployed in many cases in pilot studies only. For example, in 2011, in PJM, which is the grid on the mid-Atlantic region, they used water heaters that look like this to track frequency regulation signals. So I'm going to talk a lot about frequency regulation, but to give you an idea of what that is, the frequency of the grid is always changing a little bit, and that change is basically representing the mismatch between the supply and demand in the grid. So if there's too much supply in the grid, the frequency will increase. If there's too much demand, it'll decrease. We want them to be identical. It would be easy to solve this problem if we had lots of energy storage, but we don't. And so we're always changing generation to match demand. So the residual piece that is hard to fix because we can't get this exact matching is attempted to be dealt with in the frequency regulation market, where you're asking power plants to increase and decrease their production every 2 seconds or every 10 seconds. It's on that time scale, depending on where you are in the country, to be able to fix the frequency and send it back to 60 hertz.
Could you just repeat like when the frequency drops versus like when it's higher versus like supply and demand?
If there's too much generation, the frequency increases. If there's too much load, the frequency decreases.
Okay, thanks.
And too much relative to each other.
So you're saying the signal comes at a rate of like 2 to 10 seconds?
Yeah.
So what's with the intervals that we're seeing on the graph, the slide then?
So this is an hour, and this signal is changing every 2 to 10 seconds. But it's changing, it might be moving up in the same direction
Oh,
for
I
a while
see, okay.
versus. But if you looked at the actual points making this plot, this one would be every 2 seconds because it's a PJM. In California, I think they use every 4 seconds. In MISO, where I am, it's 10, I think, but it's about on this time scale. Yeah. So normally it would be the power plant going up and down, just with a small portion of their capacity to fix this issue, and you have many power plants doing this. But you can also do this with electric loads, because increasing generation is like decreasing load to the grid, because all we care about is the difference. So in this case, we have this water heater that's increasing and decreasing its consumption and tracking the same signal, and it's doing that for feedback control. And this has been deployed and it works. The issue is that this is a variable speed drive water heater. It can continuously modulate power consumption, so it has a variable speed drive. So that means you can tell it, go to this power set point, now go to this one and go to this one. How many of you have electric water heaters? Not many people. Most people have gas, right? How many people have electric air conditioners? Does your air conditioner continuously consume power, or does it kind of just like switch on and you hear it switch and then it produces cool, which is a funny word, or and then switch off? You hear it do that, right? So most of these types of resources, including water heaters, actually do this. They switch on, they heat, they switch off, and then the water cools in this case. And it switches on to heat again and off, right? So if you can continuously control power, you can do this well. But how do you do it if all you have is a device that is on, off, on, off? So an on-off device, which we'll call a thermostatically controlled load, a load controlled by a thermostat, which could be a water heater, a heat pump, refrigerator, freezer, all of these sorts of things, works like this. So the axis here is temperature. This is the temperature set point that you set. And then there's an on-off state here. So the temperature that you set is your target for your home, for instance, if it's an air conditioner, but you're actually going to cycle plus or minus some small number of degrees. It's never going to be perfectly there. And so the way this works is that, let's see, if it's warming up in your house, eventually you'll hit the top of what we call this temperature deadband, this area within which you want to cycle. You'll hit this higher temperature, you'll switch on your air conditioner, and the air conditioner will cool your home, and then your home will hit a lower temperature bound and turn off. And if you look at how that's consuming power, it looks like this in pulses. So it's off, it's on, it's off, and then it keeps going. The cool thing about these resources is they already have built-in flexibility, because you're okay, you're perfectly happy as long as the temperature is within this range. You're not going to notice because you're used to that anyway, it's always cycling. So the flexibility that you can harness if you're an aggregator is that you could say, this air conditioner is, the house is warming up, but now I want to consume more power. Maybe I have a gust of wind in the system and I want to consume that. I want to take it out of the system. So I turn it on a little bit early. And then we're cooling down the house now that gust is gone and I need to decrease consumption. So I'm gonna turn it off a little bit early. So as long as I stay in this range, I'm okay in terms of the house being the right temperature. I don't want to just be always cycling really fast. Do you know why? On and off, on and off, on and off. Yeah.
Burn out the motor.
Yeah, you burn out the compressor and the motor, exactly. So there are limitations, you can't just arbitrarily cycle. It's actually the case that if you turn it off, it usually has to be off for at least 2 minutes and sometimes more, just because it's pushing fluid through compressor, so. Did you have a question?
You just answered it.
Okay. Yeah, so there are limitations to this, but there's inherent flexibility built into these resources. So now this shows that instead of it looking like this, I can make it look like this, but that still doesn't help me track that very dynamic signal I showed you before. But now imagine I take hundreds of these together and I have them all do these pulses, but do them in different ways. So they each have a different pulse. So collectively they can change their consumption. So that's the feedback paradigm that I'm describing, where you have a controller controlling a very large number of resources, hundreds to thousands. If I didn't control them, they would consume this blue line over time. I want them to track a signal, this balancing signal, which could be a frequency regulation signal. And so if I control them in ways to shape those pulses collectively, they can track that signal fairly well. That's what I'm showing in this slide. Does that concept make sense? Okay. So this idea is actually what I worked on during my PhD. I developed a controller to do this, but it took 10 years to implement this in practice, and that's what I'm going to show you next. At this point in my presentation, I often get questions like, this seems like a tiny resource. Like, why don't we just build a bunch of grid scale batteries and get this job done, right? It's actually quite a large resource if you can harness the technical capacity in the system. And what's funny is actually the last time I gave this talk, I put my Michigan data up here, but I actually have a very similar plot for California, and I didn't put it up there for you, so I should have. But this is how much capacity there is in Michigan if we take all the refrigerators, electric water heaters, heat pumps, and air conditioners, and aggregate it together as a big virtual battery, and then use that as a resource to balance the grid. And what's important is 2 things. One is the scale. You can see it's gigawatt hours and gigawatts of capacity. And then the other important thing is the capacity changes over the year as a function of different things being plugged in or not to the wall, right? Our refrigerators and electric water heaters are pretty much always running in the background, regardless of the season. In Michigan, our air conditioners are not plugged in that often, just in the summer. So this is hours of the year. And the heat pumps are basically non-existent because there's very few heat pumps in Michigan because it's a very cold climate, and we're still figuring out how to get heat pumps installed in very cold climates. In California, this looks different. The air conditioners are a much nicer looking resource than they are in Michigan. And if anybody's interested in the paper we have for California, I can send it to you. But the basic idea here is it is a pretty big resource. We shouldn't just say it's negligible and that the solution is to build a big grid scale battery. So we recently had an ARPA-E project where our goal was to try to establish credibility for this type of load control at scale, use air conditioners in particular, to enable aggregations of this type of on-off air conditioner to provide frequency regulation to the grid. We wanted to do it in a way that we could actually participate in electricity markets, that we didn't cause issues in the power network by doing it. We wanted to do it at low enough cost, that it would be economically viable. We wanted to make sure that we didn't disrupt customers at all, so we're only playing in this very narrow range that they're willing to accept for temperature. And we wanted to show that overall it would be a benefit to an aggregator and the customers participating and the grid. So that was the goal of the project. It was completed about a year ago now. And we focused on frequency regulation. So this is another example. The reference signal here is another example of our frequency regulation signal. And we're trying to track it as well as possible. I'm getting questions, so I'm going to finish this slide and then maybe look at them.
Yeah, we can try to look at the later.
Okay. So we focused on frequency regulation, which is kind of the hardest ancillary service there is, because it's really fast timescale, because we thought if we could do that, we could do any grid service. So we actually just set that as our goal because we wanted to say we can do this. We can close the loop that fast. We can coordinate resources on timescales of 2 to 10 seconds. And we have to, doing this type of service requires coordination because they have to work together. It's not a distributed service where everybody is responding independently to frequency grid.
I was wondering, what kind of equipment do you need to, if you have a refrigerator or like a thermostat to participate in that? Like, can you just retrofit like
Yep.
old devices,
Yes.
or do you need a new one?
You don't need a new device. All of the existing devices work. You just need to talk to the thermostat. And the thermostat has to have some communication and computational capabilities, which they're already capable of doing, but they're not all enabled. But I'll talk more about that. It's a great question. Mhm.
I just have a quick question. I think 2 slides back, I was wondering what the peaks are. It looks like the lines are the total capacity in gigawatts and gigawatt hours, and then is that demand?
The peaks,
Yeah,
the peaks like these spikes.
yes, yeah.
The spikes are when the air conditioners are plugged in and operating. You get way more capacity from this battery.
Okay.
Yeah. And then it's broken into the power capacity and the energy capacity, how long they can store energy. Refrigerators are really good at storing thermal energy, whereas other resources less so. Yeah.
How does this compare to the total demand for capacity in
In Michigan, I don't remember off the top of my head. California is 60 gigawatt peak, is that right? Does anyone know off the top of their head?
I think 52.
52,
When it gets really bad, I can get to 80, but that doesn't happen often.
80, okay, so 50 to 80. Michigan is smaller, I would say half the size.
I'll read the questions online.
Okay.
too. Yeah, so the question from online is for the frequency regulation signal, is that sent out to the ERs or aggregators from the utility? And is that signal the same for all resources participating, or is there a unique signal to each aggregator? For example, based on what capacity they have to respond?
Yeah, that's a great question. The signal is sent out from the independent system operator, not the utility. So that would be CAISO, MISO, ERCOT, New York ISO. Those are examples of system operators. The utilities actually aren't involved in this kind of wholesale market piece of balancing the power grid. And that is it the same signal? So it is the same signal sent out to all resources, but the resources scale it by their capacity to respond. So every resource will have a different capacity of its response, but otherwise it's a unitless signal. And then you multiply it, like if you offer 10 megawatts, you multiply it by 10 in your case. But then so the aggregator gets the same signal as everybody else. And then the aggregator can disaggregate that signal to send different signals to different resources if they so choose. Because they might know that I don't want to ask this air conditioner to respond because I know today that one's not on. So I'm not going to send that one anything, or I'm going to send different signals throughout. But they get to choose how to do that. So the way we address this problem of designing and building and deploying this system was we built a simulation test bed where we could simulate an arbitrary number of air conditioners using very high fidelity models of air conditioners. We also modeled the distribution networks and the communication networks, and we made everything very configurable so that we could change it. And it doesn't have to be 1,000 air conditioners; it can be as many as you want.
This is only residential too, right? This is not.
This is residential on-off air conditioning. And you should think whole home air conditioning. You could do this with the window box air conditioner, but the thermostats really are not ready to do that. So whole home, yeah, residential. And then we built an experimental test bed at Los Alamos National Lab. So the picture might be a little hard to parse, but each of these blue boxes is a model home. And the homes are stacked because we didn't have very much space. And each of the homes is cooled by an air conditioner and also has an internal heat source that was actually a water heater that we're using to emulate the internal heat load in a home. And we actually implemented all of this and controlled everything through a lab view interface, working with staff scientists at Los Alamos. And then we did a field test where we were working with partners at Pecan Street, which is an Austin, Texas-based nonprofit that does a lot of demos and energy work with a specific, relatively new community, and that was built in Austin maybe 15 years ago. So a lot of the homes in this community have solar on their roofs and are just happy to sign up for demonstration projects. So it's a great group to work with. So we enrolled about 100 real air conditioners, and we built a bunch of hardware and software, and I'll explain a little bit more what that is. But the hardware was pretty minimal. We're basically just trying to emulate people's thermostats. We used data from the field test bed to validate the experimental test bed and the simulation test bed. We were also able to run experiments on the experimental test bed that could be much more aggressive than the ones you can do in the field because you didn't want to upset these participants. But here you can do whatever you want because there's nobody there. So we learned a bunch of stuff from those very aggressive experiments and used them to improve our simulation test bed too. And then we close the loop. We, now if we want to control a population of air conditioners, so 100 air conditioners isn't actually enough. If RP had given us another $5 million, we would have done probably 500 air conditioners, which actually would be a big enough resource to participate in the market. 100 is probably not enough. So what we did is we made it so we could do something hardware in the loop with the simulated ones and the real ones. So we can make an arbitrary size population, and they were working together in real time. So based on what these actually did, it would change what we asked those to do and vice versa. So live, they were working together, and we also can make those work together, the simulators and the experimental.
Just a quick question, so all of them were doing pre-cooling, like that's the only, or what was like, how they were, how you guys, like, what was the control signal actually?
The control signal was switching them on and off within this deadband
Across what was the objective?
to track the frequency regulation signal.
Oh, that's thank
Yeah, so it's switching on and off, it's sending switching commands.
you. Okay.
Mhm.
Is this more or less effective in systems with like existing pre-cooling measures?
If the system already can do pre-cooling and it has the software built in to do that, maybe it's a little bit easier to talk through them, but like any Nest, Honeywell, ecobee thermostat can do this.
I guess I mean
So-
like with respect to like energy savings or like the capacity availability.
The capacity available. So pre-cooling is useful for the grid, but it won't allow you to provide frequency regulation. So it's a slower timescale service and there's not good compensation mechanisms. You could talk to your utility company if they offer demand response and you could get incentivized to do that. Frequency regulation you offer to the system operator like KISO and then get paid for that flexibility. So it's a more complicated service and possibly more valuable service. Mhm.
I'm curious, the generators that are currently within frequency regulation, other ancillary services, if there's some kind of incentive to try to shut these types of aggregators down because they're being paid to provide
If
those
they're
services.
being paid. Yeah, I mean, if the generators are making a lot of money providing frequency regulation, then they maybe don't want this type of competition. I mean, it's possible, but generators also get paid a lot just to provide energy. And if they don't provide frequency regulation, they can provide more energy. So the way electricity markets are dispatched, power plants are agnostic to whether they provide more energy or less energy plus frequency regulation because they're covered for those costs.
Yeah,
So maybe they wouldn't care.
I thought, maybe I'm wrong, but I thought that in a KISO, there's some generators that basically are only in like ancillary services. So they
Only
would-
an ancillary? Okay.
Yeah, so they would, I could be wrong, but I'm pretty sure that that's true, so they could be kind of put out of business. But yeah, I don't know.
While it's physically possible, I'd be very curious to know if this actually happens because.
Yeah, I could be wrong.
Yeah.
I just want to say, like, the demand for flexible, like, frequency regulation is way higher than current, like, capacity. So adding
Why?
DER flexible, like, capacity for frequency regulation wouldn't take away their ability to do, like, it wouldn't, it's not a small market, like, a lot of it needs, especially with additional reuse.
Yeah, and this is really looking ahead to like in the future when you need so much more of this.
Yeah.
Because of renewable integration. Yeah.
I understand how like load shedding and load shifting have a material benefit, but frequency regulation feels more abstract. I guess hearing a couple people say that it provides a lot of value, but I don't understand that value.
So frequency regulation drives the system frequency. So technically what it does is it just drives the system frequency back to 60 hertz. And it does that because if the frequency deviates too much from 60 hertz, it starts to damage equipment in the system. So it's a technical requirement to avoid equipment damage. And it's not just equipment damage, but if the frequency starts to deviate, it can also lead to blackouts eventually if you get kind of rolling effects. So you're preventing these like big things from happening or equipment from being slowly degraded because it's dealing with poor frequency over very long times, right? So those are the things that this is helping with. And to do that, when they bid into the market, they get paid for the capacity frequency regulation they provide, and the market prices are fairly high compared to other markets because it's such a valuable service, because it's hard to do. Yeah.
Okay.
So like, this requires almost millisecond, like switching
Second, yeah, second level, yes.
second level, but I mean, a lot of internet connections are not
Mhm.
stable over time? How is this type of system accounting for that variability and,
Feedback control. So the key thing here is any individual device, air conditioner, is not going to be responding every second. It's going to be responding every few minutes. But at any few seconds, some of them are going to be responding. And if some of them are late to respond, I'll see that because I'm collecting data from the system, and then I can adjust my next control command to get more response or less response. So it's all about closing this loop of seeing what's happening and then adjusting. And it's never perfect. And I'll show you plots that show it's not a perfect thing, but it's pretty close, and it's actually often better than aggregators.
and I'm guessing there's just some default behavior that if it doesn't get a command in some area, that it just continues normal
Yeah,
operation?
it just keeps going. Yep,
Okay.
yeah, exactly. And another resource might jump in, right? Because you're gonna ask for more from somebody else. Yeah.
So it seems like your real like control there is you can quickly turn them on,
Or
right?
on.
Well, maybe not. You said, there may be limitations for like how long it can take to turn something on, or sorry, turn something on.
At any given time, some of them might not be able to turn on or off because you have to protect the compressor. But some of them will be. And so you're turning some of them on prematurely or off. So you have control both directions.
Okay.
Yeah.
Oh, okay.
Yeah. The key is large numbers. If you do this with 100,
Yeah.
you might run into situations where none of them can be responsive. If you do it with 10,000, you're gonna have much better luck. Yeah. Let's go here and there. And then I'm gonna get back to this. Come back and then more questions.
This might be something you're getting to, and it seems like it's less important with the frequency of regulation, but
Yeah.
is there like a spatial thinking about like where you're taking
Yeah.
the load up? Oh, okay.
There could be, but it depends on the market. So there's different zones for ancillary services. So it does matter that you're balancing here and you're balancing on another part of the grid. But with frequency is pretty much a global signal in the grid. If you measure the frequency anywhere in the Western interconnect, you're gonna get basically the same frequency, unless there's a big event happening and there's like frequency waves propagating, which doesn't happen very often.
So the spatial thinking would be for like capacity programs.
Capacity, or if there's larger ancillary services, like you want a lot more response, and that response might be problematic to deliver if there's capacity constraints on the transmission lines. But these are small tweaks to the system, so we assume that the transmission line constraints aren't gonna disrupt it. So you can kind of get it anywhere from the system.
Yeah, thank you.
Okay. So when you design a controller for this, and maybe this will answer some of your questions, the goal is to track this frequency regulation signal, which is a power signal, as well as you can, or at least as well enough as you need to satisfy the criteria that the system operator, the ISO, requires. You have to keep each home's temperature within a narrow range around the temperature set point so they don't notice at all that you're doing this. And your inputs are these switching actions, whether or not to switch each TCL or air conditioner every 2 seconds. There's a lot of papers on this. There's thousands of papers that develop different methods of control. I'm going to just mention two quickly to give you a flavor that they can be very different. There's an approach called packetized energy management, which came out of the University of Vermont. I say and subsequent publications because they have at least 20. You can read all about this method, but the idea here is that the desire to switch actually comes from the consumer. So an air conditioner that wants to turn on or is about to want to turn on says, I want to turn on. And the aggregator decides how many requests to accept to shape the load. So you have to start requesting to turn on before you absolutely need to turn on, so that you don't get into a situation where the home temperature goes outside of range. So you start asking early and you hope you get deployed. And then eventually, if you get to a point where you just have to turn on, you turn on. But the aggregator has control because they choose how many requests to accept. And this is an anonymized sort of process. They don't know who's asking, they just select randomly. So that's one way of doing this. The way that I worked on in my PhD was a top-down way to do it. So we developed a model of the dynamics of air conditioners and how they move around their deadband. So I showed you a deadband earlier where they were switching on and switching off. This is the same type of plot. But here, now imagine you have 10,000 air conditioners moving around in this space. They have temperatures, they have on-off states. I can discretize that space and turn it into these bins. So some of them are going to be off and in this temperature, some of them are going to be off in this temperature or on. And I can keep track of how they move around this space dynamically as they're all cycling. And I can actually represent that with a Markov transition model. And then I can derive a model of the system that looks fairly nice. It's a linear time varying system. So if anyone has taken control systems, you'll recognize this as kind of the starting point for a lot of control, except we usually assume A is not a function of time. K is time. Okay, usually A is fixed. Here I'm saying the transition through all these different spaces changes with time because outdoor air temperature is changing. So that's going to affect how these devices are moving around their space. But you can write this model and then you can use this model to predict how many air conditioners are in each state. And then you can direct your control actions to specific air conditioners. I might want to say, if you're in this state, you're going to turn on soon anyway. So why don't you turn on a little bit early, but I only want 40% of you to turn on early. And you can send that as your control command and get a response. So it's a top-down approach where you have a model and you're directing control commands based on that model. And using feedback to estimate or measure how many air conditioners are in each of these discrete states. So that's what we actually implemented in our field test.
I was curious, does this model require more kind of like air conditioner specific information because you're actually tracking where exactly it is rather than just randomizing?
Then the last one?
The last one.
Yes.
Yeah. Okay.
But it could involve observing input-output data over time. Like it could, as opposed to having homes report to you, there could be ways to get this through data that you observe from thermostats. So it's not a burden on the person. But yes, it does require more information because you have a model. The other one doesn't have a model, but the problem with the other one is they have no idea how much resource how many requests they might have in the next time step. It's just random each time to them and they're deciding. So they might run into a case where they can't shape the load anymore because nobody's asking. Yeah, so pros and cons. This one also you can set up so that in real time, you don't actually need any information from the loads in real time because you're using the model for estimation and you're just measuring something on the grid to get kind of that feedback signal. Whereas the other approach requires two-way communication with every resource. So the communication requirements of the other one are heavier than this one. Models help reduce that, right? So that's kind of the main message. Yeah.
I was just curious, in your test bed, did you have any solar tie-ins as well, so that you could get maybe data as well from the like grid tie-in inverter?
Interesting. Some of the homes had solar for sure. Actually, many of them do, but we weren't using the data in real time.
I'm just
One
wondering
could.
what the feedback
It would
was.
be cool. Yeah. Yeah, because you would get voltage data, for instance, as well. Yeah, exactly. Yeah. How are we doing for time? I'm getting lots of great questions. Okay, and I'll try to stop a little early. So this is what we implemented, and in terms of how we had to do it, this is what it looked like in terms of the hardware. So most homes in this community had a Nest thermostat. And if we had a partnership with Nest, and if they opened their API, their application programming interface for us, we could have done everything inside their Nest, but that wasn't possible. So basically we bypassed their Nest thermostat. We built our own thermostat, and our thermostat looks like this. It's like a Raspberry Pi based board that intercepts the signal from the Nest so we know what the house wants to be doing. And then it sends the commands to the air conditioner compressor to directly control it. So again, this doesn't have to exist. All of this could exist in there, but this allowed us to talk to the homes every second if we wanted to and know what the home wanted to be doing, but we could bypass what the thermostat was saying and do our own thing.
Did it need it to be like a smart thermostat or something like that?
It would need to be a programmable communicating thermostat, which in California, you have a standard for this. So all new construction has to have this. Most of the country doesn't though. But if you have a programmable communicating thermostat, you could build all of this in. One of the major hangups, again, is opening up the API so you can actually make the thermostat do things. And most thermostats only take changes as temperature set point changes as opposed to on-off. So remember, I'm turning this thing on, turning this thing off. But usually the way you set a set point is through your temperature set point. But the thermostat actually turns the temperature set point into an on-off command. So it has the capability to do it. So again, there's no fundamental hardware challenges here. And we use their existing air conditioner. We didn't play with the air conditioner itself at all.
What kind of challenges are introduced by how long it takes the home to reach the desired temperature you want it to be at?
The home's temperatures aren't changing. They're always in this narrow range. The home sets its thermostat temperature to a specific, whatever it wants, it chooses. But then we're cycling it within this range, plus or minus a degree that the thermostat already uses. So there's not really challenges there. I guess I could interpret your question as if it's cold at night, maybe it would take a while for them to actually switch on their air conditioner. There
once
could be
they're
cases
within
like
that band,
Yes.
it's just a simple
Yes.
constraint, I guess.
Yes, exactly. Once they're in the band, it's fine. If the air conditioner is off because you don't need air conditioning now, there's not much you can do. And if any of you work on like electric vehicle control, it's a very similar problem. It's like the vehicles come and go. When they're not there, you can't do anything with them. When they're there, you can schedule their charging. Air conditioners, same thing. The homeowner is choosing when to plug it in and what their set point is.
Is Nest not opening their API because they're offering their own aggregation services or?
Nest has a closed API. I think at some point they had it open and then they closed it because they all wanted to do this themselves.
Okay.
We've had many conversations with them. It's kind of a one-way street where we tell them stuff and then they're like, okay, thanks. I mean, I had my first conversation with them in 2012, right? And so many since then. So I don't know, but I don't think they're offering this sort of thing right now. I think that the perspective from the thermostat manufacturers is, this is really cool. They could definitely do it. They're still not sure if the cost benefit works for them, given how much they have to engage with consumers to get them signed up and the money that they earn from doing this. But this is why this is research, because in 10 years, I think that those cost benefits will change.
So just to make sure, on the air conditioner level, the control is only to make sure like the temperature is between those two bounds, upper and lower bound.
From the home side, the temperature always is between those two bounds, yes.
So,
We're not changing the home's average temperature at all.
okay, and that's the user preference, they are setting that.
They said that.
And then whatever left behind or whatever, that's what you can control, right? Because-
All I control is when it cycles to maintain the temperature.
Okay. Because I'm assuming if these are 100 ACs and you are trying to, let's suppose they are connected with one transformer and you are, or somewhere, and you are trying to maintain the frequency, right? By turning some of them on and off whenever the frequency is going up and down.
Mhm.
But on the other side, the consumer don't want to be disturbed by.
And they won't notice here because I'm maintaining their temperature so tightly. They're never gonna, it's actually, I'm maintaining it more tightly than their existing thermostat does. And I'll show you that.
The thermal model that we're showing, is there any supervisory control behind that that's doing between the bounds, like how, what is the control method?
The controller, this controller is modeling this state space of this.
Yeah.
And that embeds the bounds.
So when you model, let's suppose if I model this space and I want to keep temperature between two bounds.
Yeah.
I have to put some control there to make sure like those states are not going out of those bounds. So I'm just talking, what is this? What kind of algorithm is there?
I'm struggling with how to answer.
Okay, so this is your thermal model. Let's suppose this is the thermal model of this space.
This is the thermal model of hundreds of this type of space.
And this is like kind of 100.
Or thousands of this type
Yeah,
of space.
exactly. So I'm
And-
assuming,
Imagine we keep the room here between 70 and 72.
Yeah.
The room will always be between 70 and 72. I hear the air conditioner on right now. But the thermostat in this room will just switch the air conditioner on and off and modulate the temperature all the time. And that's what it's doing. Actually, this
okay,
this
so
room's not a
which
good
means
example
there
because
there
this is a
no-
different kind of air conditioner.
Okay, there is no control on the air conditioner then, or no feedback control on the air conditioner itself.
It's its own control on its own set point. So when it reaches its set temperature beyond that point, it turns itself off a bit.
Just the way like the air conditioner is working.
The way the air conditioner is working does not change. We're just changing when the thermostat tells it to cycle on or off. That's all. So we don't do anything to the air conditioner. The air conditioner receives controls from the thermostat. And we're just slightly playing with the timing of the cycling. Yeah, back there, and then I'm gonna move on.
Temperature in the balance in that model.
Sorry?
How is that model maintaining the temperature in the balance here? Feedback on home?
Yeah,
Yeah, so because the model assumes that the air conditioner will switch if it hits the end. So basically, the way that could be implemented is that if you hit the bound, the controller needs to let you switch.
yeah, that's.
And it doesn't model the states outside of the bound, so it just happens, the switch happens automatically. Or I can force it for any time, I can make that happen by saying anytime the air conditioners are in this state, I force them on because they have to be.
So you can make it come on early, but you
Can't make it come on later
can't make.
because you're maintaining.
Yeah.
And it's a decision. You could choose to go late by, I don't know, you could make some choices to add more flexibility and that would give you more capacity, but it would be a trade-off for the consumer. So here we're saying no, but it's a choice in a control design. So let me show you how this looks. So the blue is the regulation signal on the top plot, and this is over time, how the power of aggregation of air conditioners is changing. This is about 100 air conditioners, half of them virtual, half of them physical. And we're trying to track that blue signal as well as possible. And you can see, and this is for, you know, real hardware in the loop experiment. You can see it's not perfect, but generally it does approximately track it. And here we split it up where we show the real air conditioners that are actually in the physical field test bed, and then the virtual ones that are in the simulator that are working together. So the sum of these two is then that red dashed line at the top, working together. And what we did was we said, we did 4 different runs of that test in 2023, and we computed how well we can track that signal. And PJM, which is again the system operator in the Mid-Atlantic region, requires these scores to be 0.75 or higher. That's a metric for how closely you're tracking the signal. And we found for each of them that we're well beyond it. So these air conditioners are capable of doing at least as well as a power plant to do this. So it works if you trust our hardware in the loop simulation piece of it, you know, because it's half simulated, half physical. But again, they're working together in real time. We're not just using the simulation after the fact to correct the physical. That's not. And then what's the effect on the end user? So for each of those experiments, we said how much is the air conditioner switching on and off during our experiments versus when we're not doing experiments. So we slightly increase how much switching we're doing because we're switching a little early each time. Okay, so switching goes up, which places a little bit more wear and tear on the compressor. Then we look at how well we're regulating the temperature within the range that we try to stay in. Normally, it's regulated so that there's like a 0.9 Celsius band. We actually regulate it more tightly because we're switching earlier. So we're actually basically providing a more precise temperature set point tracking to the home. But that's not necessarily what they want. They don't need it to be regulated that tightly, but we can do that. This is how often we violate the temperature deadband. That means people feel too hot or too cold in their house. Normally, there's this type of 10 to 20% of the time it's a little too hot or a little too cold in your house. We regulate it more tightly because again, we're tracking that temperature set point more closely. So we actually provide better comfort service to the house. Is how you can think of it. And then the last one is energy consumption. During the experiments, the air conditioner usually consumes this much. During our tests, it increased, but there was an experimental design issue where the signal we were sending to them was actually biased. So we were actually asking for an increase in consumption. So I wouldn't place too much stock in that number. This paper here describes this more comprehensively and it talks about like how you could get rid of that. Yeah.
Yes, so when you try to control the thermostat, are you intercepting the signal that the control system of the air conditioning sends, or are you implementing your own logic?
We're intercepting the signal from the air conditioner, but then we're bypassing it. So we implement our own thermostat.
So you have the information on what the control signal is sending, and then you delay it, or you.
Yes, yeah, exactly. Okay, and then because I thought you might be interested just in terms of like how hard is it to get people to sign up to do this? You might already be thinking, would I do this? Would I let somebody else do this? We approached 309 households to participate in the study. Half didn't respond. 90 received the installation and actually got going. So some of the houses, like we went in and were like, oh, your air conditioner has a problem, or your circuit board has a problem, or your thermostat has a problem, and we can't work with that, right? So the ones that worked was 90. So we aimed for 100 and we got 90. And I say participation during experiments was 50 to 60%. You might say, oh, people are opting out. It turns out like almost nobody opted out. We got a maximum of 2 opt-outs during one test, and most tests had no opt-outs because everything's automated and they can't tell what's happening because we're maintaining the set point. They just don't see it, right? Which was the whole point. But the reason why participation was low is because of the hardware software. It was that the data didn't come to us on time, so we couldn't prepare them for the test. Or the communication system went down, or their home Wi-Fi was down and we couldn't talk to their device. So it was all on the technology side, why they didn't participate.
What type of feedback did you get from the actual users or the occupants of the home say like they experience it was too high, even though your control.
So I would love to answer that question. So the reason I'm hesitating is because this is a technology demonstration and we didn't technically get human subjects approval, even though we worked with our human subjects office on this. So we're not allowed to share with you what people thought. But at a very high level, like I said, nobody noticed. Without getting into details.
Probably the greatest
With custom hardware like that, though, you can, you know, have a variability of, say, like software versions across,
Sure.
you know, the Raspberry Pis, or you could have, you know, even time synchronization issues amongst them, or like, was there any cold starts, say, of like power grid during that time, so that like you could see how it responded to complete power shutoff and coming back on?
Oh, I see. So the tests were like 4 discrete hours over the course of the summer. And if there had been a major outage in the neighborhood, we would have waited for everything to kick back on and then we would have gone, right? So we wouldn't have tried to test it under those circumstances, which is very important to do, to see how it fails, is what you're saying. But yeah,
Okay.
Yeah.
Just even the time synchronization of the Raspberry Pi takes.
like when they all are coming
Yeah.
back and yeah. So we basically were probing the system to see how many were online before we'd initiate a test.
Okay.
So we avoided that. It's important for in practice to get that sort of stuff to work. Yeah. I thought you were asking about what people thought about their engagement in the program, and that's the part where we actually
I wanted to know that
had some
too.
information and then we're told to pull out a paper. So it's like, yeah.
Sorry.
No, all good. Okay, so just as a summary, what we did was we showed that these aggregations can provide frequency regulation with very minimal impact on the end user or the compressor. There's a lot of practical challenges. That paper that I was citing talks a lot more about the practical challenges of getting this implemented and what we had to do to make it work versus what you would do in practice if you wanted to deploy this commercially. So that's what we focused on there. And that, again, you can do this all within a smart thermostat. It doesn't have to be, it's not a fundamentally difficult communications or hardware challenge. It's more of a software coordination control challenge. And we put all of our code, including our simulation testbed and all of our controllers in a GitHub repo, which is open source, so you can use it if you like. You've asked so many great questions that I think I'm just going to give you the highlight of the last section and not go into too much detail because I want to stop and leave room for more questions. But the last part is I just want to talk about other challenges that we work on. So specifically impacts on distribution systems and how you can get the utility involved, because there was a question about what is the utility doing here? You're talking about the system operator, which is like the market operator, but the utility like PG&E, they're going to care about this too because it's going to impact their network. So that's what I've been working on for the past 5 years. Actually, this other work was like 15 years old, plus we finally got to demonstrate it 2 years ago. And now this is actually the kind of like more intellectually stimulating piece, I think, right now. So we all know that if there's too much solar PV in the system, it can cause problems, right? You put too much solar PV, the voltages increase, the power can flow backwards, which the system wasn't designed for. If you have too many electric vehicles connected to the system, the voltages can decrease. It can also overload transformers and cause heating problems, which then can make them have a reduced life. All of these things can also happen if you coordinate DERs improperly. So if you synchronize them and get them to work together and then they're all on at the same time or off at the same time, it's a little bit like having too many EVs or too many photovoltaic injections into the network. But the problem is most aggregators, so we've talked about how car companies can be aggregators, or thermostat companies can be aggregators, but other companies can also be aggregators. They don't have any visibility into the actual network because they're not the utility. And the utility can't share that information with them, because the utility has to protect that information for privacy and security reasons, because they don't want people to attack these networks. That's essentially what it is. So there's this issue of who knows what and who's affecting what. And so as an example, if I have a bunch of air conditioners and I'm controlling them, and normally they would consume this much power, here they're consuming this much power because I'm using them for frequency regulation, it causes fluctuations in voltage. So we have 3 different cases here where we have the base load in the network low, regular, and high. And you can see sometimes those fluctuations lead to voltages outside of these red bands, which are the nominal limits of the system that you need it to stay within. So if the voltage goes too high, it could damage equipment. If it goes too low, equipment won't turn on. It also can cause overloading in terms of the transformers, which leads to transformer aging. Okay, so all of this can happen. So how can we avoid these types of issues? So one way to avoid it is to ban aggregators. And that might sound crazy, not have aggregators. We don't want them on our networks. California used to ban aggregators, but they came back many years ago. Michigan banned aggregators until very recently. But then the federal government put in place a order called FERC 2222 that requires independent system operators to let distributed energy resources participate in electricity markets. So states that had these laws banning aggregators had to remove them from the books because now they're not consistent with federal law. If you're in again, there's a lot of caveats to that. So if you're in certain parts of the country, that doesn't apply. But where you are and where I am, it does. So now Michigan has to figure out aggregators, and the utilities are afraid because they don't know how to interact with these companies that are going to start to impact their networks. And then there's this global conversation about this because we're talking about this everywhere. And in Europe, they're talking about transmission system operators and distribution system operators having to work together. So for this is our independent system operator and our utilities. They need to work together. So they're actually thinking about it as a coordination at the highest levels of grid operation. In Australia, they're thinking about it bottom up, where Australia has a lot of solar PV and it's leading to problems in distribution networks now. So the utilities are constraining the solar PV injections into the grid at certain times when it causes problems by using a concept called operating envelopes. So basically saying, you have to curtail your solar PV at this time because you would cause problems if you didn't. And they issue these envelopes which change over time based on the network conditions. So that's what they're talking about. And we talk about a very similar issue here called dynamic hosting capacity. So hosting capacity is how many of a resource I can add to a grid before the grid starts to fail. Dynamic hosting capacity is how I can use the resources until the grid starts to fail. So hosting capacity has stopped solar PV development in certain parts of the country, like in Hawaii, because everyone wanted to buy solar PV in Hawaii because the electricity prices are so high. And the utility put a pause on a lot of neighborhoods because they had to upgrade the system first. But if you build it, but then can control it, so you can make sure at key times there's not a problem, it allows people to build, even if the grid can't serve on the worst day of the year, because you're going to use control at that point in time. And then the way we're also talking about this in the US is this issue of how we think about aggregators and interaction with utilities and this FERC order. So this is the Federal Energy Regulatory Commission order. So if you're interested in the policy of this, that's where to look.
Would combining batteries with solar open up some of those challenges?
All of this could help, yes. But then most utilities won't let you build something if it can't, the grid can't handle it in the worst possible case. So controls, real-time controls are not sufficient to say, let me build this thing because I'll control it if there's a problem, because those communications aren't all in place. But yeah, I'm technically, yes, we can solve this problem. Like the regulatory environment doesn't always allow it. Yeah.
Thanks. Is there any potential?
Yeah, go ahead and then I'll wrap up really soon.
Okay. Is there any potential for combining relatively small battery storage with these, you said thermostatically controlled loads, like attach a small battery to your air conditioner or to your heat pump controlled water heater, and that way the grid simply doesn't see that synchronized load of weather.
If you get more controllable resources behind the meter, absolutely. Or you could coordinate your air conditioner with your water heater so they don't flip on at the same time. Like you don't always need to add another resource either. You could do a lot behind the meter to make the house look nicer to the grid. Yeah, absolutely. So let me share just one more slide to make this issue more concrete, and then I'm going to skip my last bunch because you've asked such great questions. But I just want to highlight just one more way what this issue is. So we have the system operator that receives bids from power generators and then dispatches them. This is how the grid is traditionally worked. Grid generators say, I will produce this much power. The independent system operator, like Tyson, dispatches the system. Now we have DER aggregators enabled by this FERC order that say, I want to play too. I want to offer energy and ancillary services and participate in the market. And now I'm going to get dispatched to do that. And then I need to coordinate DERs like air conditioners. So this part you've already seen. But what we never looked at before was where on the grid do these things exist? So it's funny because there's a box here which you cannot see, which is blue, which says that generators and the independent system operator are basically transmission system. All of these are connected. But these are in the distribution system. The independent system operator has no visibility of the distribution system. the distribution company does, your utility like PG&E. And so these are doing weird things now to our local networks, like the lines that go down the streets, and we need them to coordinate with each other. So I will stop there, even though I have some cool stuff about how we figured out how to solve this piece of the problem. But I think the key point here, let me just move to the end, is that I don't see my cursor. Oh. Is that the best strategy for that coordination between a utility company and an aggregator is still completely an open question. I tell my students who want to work with me on this, like, it's the Wild West now. Everybody is proposing, oh, but what if they share this information? Or what if we send, the aggregator has to send the information to the utility to make a decision, and then the utility will execute the controls? Or what if it goes the other way, where the utility says, this is what you can do, and the aggregator has to stay within those constraints, and then that goes, there's all these different options. So it's a really good space to think in right now, because nobody knows what's gonna happen. And I think every market is gonna implement it differently. So it's a really cool problem. And then I capture that again here, that this network awareness, how to make sure you're not impacting the distribution network is still a key issue. But I think these are the remaining challenges in this space. We don't know how to think about making sure we protect the distribution network if we do what I was showing you before at scale. The regulatory environment is evolving, and a lot of good ideas that you brought up and that I brought up aren't enabled right now just because of the regulatory environment. So we need to like work with these people to also move the needle. Interoperability is an issue, like I talked about APIs and consumer adoption of these types of technologies. We need to build trust with people. I'll stop there. Thank you.
Okay, so thanks for the great presentation. And also I have two quick top-level questions, and it's really simple. So I'm not sure, like, regarding for the electricity market, like, when you talk about the price, normally what kind of price are you considering, like, they're high or real time?
It could be either. So when you
Okay.
talk about electricity markets, there's capacity prices, which are years ahead. Energy market prices, which are day ahead and real time. Ancillary services, day ahead and real time.
Okay.
Frequency regulation is ancillary service. So the price is for the capacity offered in real time, but it's usually negotiated day ahead.
Okay, so second one is based on this, so they ahead and also real time, most cases a wholesale price, right? Like regarding for my research, like I use that they ahead and also.
These are all wholesale. Yeah,
Okay.
it's all market. So markets imply wholesale. Yes.
Okay, so how about retail? Have you seen about that before, like?
So there aren't competitive retail markets. There's
Yeah.
retail prices, right?
Yes.
And then
yes.
you have utilities offering prices to consumers and consumers choosing how to consume or produce and so forth. Yes, I mean, you can also do that with these resources and participate. It's a different paradigm. It's also harder to monetize as far as I view it, because
Yes.
the wholesale market is kind of where the prices are interesting and fluctuating, and they're not as heavily regulated as retail prices, which are very stable.
Okay, so.
Yes, but you can do controls in the retail market, sure. It's just not really a market.
Okay.
Go ahead.
For interoperability, like, do we have something like a tool to connect the device to the communication grid, or do we have to like change the equipment to fit in the communication line?
So an example that I gave you, if you're using a programmable communicating thermostat, it's already communicating through the home's Wi-Fi to the internet, and then you can basically communicate it through that. A lot of solar PV systems and other inverter-based resources are connected again through Wi-Fi to the internet at homes. So I don't think you have to fundamentally design new communication systems. You could do something faster, more reliable, or that doesn't require the home to have Wi-Fi, for instance. But it would cost more, I think. So there's trade-offs there, right?
Let's go back to slide 26. Sorry, it's kind of in the middle, but. Oh, maybe more to 27. And, yes, this one. So I'm interested in one when you say on the right side, energy consumed. So you say that there might be a bias here that after the experiments, the energy consumption, after you controlled it using the controller, the energy consumption increase, which is correct me if I'm wrong, but from what I heard that so you're doing the controlling so that to make it until the 60 kWh, right? So it doesn't degrade the devices. But I really wonder why after you use the controller, then it becomes energy consumption is higher instead of energy saving.
So pull this apart a couple ways. There should never be an energy saving from this. It should always be the energy use is about the same as it was before, because essentially all this is doing is load shifting. It's just doing really like complicated fine time scale load shifting. It always should be about the same. What I was trying to explain here is the reason why there's an increase is because the signal we sent it had a bias itself. So we were asking it to actually consume more because we didn't check that the segment of the signal we were sending would lead to the same energy consumption as in the uncontrolled or the baseline case. And so I don't think this additional energy consumption means that if you participate, it's going to increase your load. It should be almost exactly the same as it was before. It's just the instantaneous power draw will shift. But the reason why this was interesting to our team is because I've done a lot of work on commercial buildings to understand if commercial buildings do load shifting, does it increase their energy usage? And I'm fairly convinced in that case that it does, because when we do load shifting, the building operates a little less efficiently, and that can increase the building's energy usage. So then you have to say, well, is that okay? Because you're also providing a benefit to the grid. Is the benefit to the grid bigger than this detriment due to the increased energy usage? Happy, I could talk about that one for hours, but yeah, I'll leave it there.
I was wondering, so a lot of this seems like an incentive to suppliers, but trying to look at, I know you kind of briefly mentioned it at the end, but the incentives for consumers, and I'm wondering kind of outside of new construction, what are you looking at to try to incentivize homeowners or consumers to be able to implement some of this technology? Because I don't know if it provides.
It doesn't require new construction at all. I mean, it's like, again, you just need the thermostat to have a software upgrade, that's all. But you get paid. So like the aggregator would pay people and say, if you sign up for my program, you get $10 a month, $50 a month. I don't know what the right number is. But they would need to make sure that that money was coming from how much money they were getting from the electricity market to make sure it was covering their costs. So that's a big question. Is it going to cover their costs? Are they going to be able to pay everybody enough to participate? But we would not be asking anybody to do this for free.
So a little bit of a follow-up from that. So are you looking at the aggregators being the ones to incentivize, or would it be like a federal subsidy?
It could be through policy, but it could be that, so there's a bunch of models for this, but what I showed you here is more like the aggregator needs to figure out if it's going to make enough money to then distribute that to get people to participate. But you could have something that says okay, so in certain parts of the country that don't have a lot of air conditioning, every new air conditioner is sold with this already built in, this capability, or in every new thermostat. And if you buy this thermostat that can do it, you'll pay half the price versus if you buy this thermostat that can't do it. So then that could be part of a standard or a subsidy policy or something like an Energy Star, right? Which doesn't exist anymore, but I don't know. But like it could be totally built into policy. But here I'm just assuming that policy is not going to come. And is there just enough money in markets to justify this already?